In this lesson, we will start by identifying the most common causes for overstressed locations that you will come across during the design and assessment of piping systems. We will discuss excessive support spacing, insufficient stiffness in the system, insufficient flexibility, inadequate piping for the design pressure, dynamic effects, and settlement. Let's start with excessive support spacing. In order to discuss this cause of excessive stress, we take a look at our model and zoom in on the indicated horizontal pipe stretch. Here we see a side view of the pipe stretch. The relevant piece of the piping system is indicated with blue pipes. All other elements are grayed out, including part of the storage tank in the background. The shape that pipes attain as a result of gravity is similar to the on-screen shape. This shape is exaggerated for visualization purposes. If we look closely, we can see that there are sharp geometric changes in the piping at the pipe supports. These are the locations where the highest bending stresses occur for these long horizontal pipe stretches. The sharper the bend, the more stress is observed at those locations. When pipe supports are closely spaced, the pipe span is shorter. As we have seen previously, this results in a lower vertical deflection at the midpoints between the rest supports. A lower vertical deflection at the midpoint between the rest supports means that there are less sharp bends at the supports and, therefore, lower stress. However, when the pipe span is increased, these bends become sharper and sharper until the stress is increased such that the allowable is exceeded. So, to identify whether this mechanism is the cause of overstress in the system, you should check whether the overstress locations are in the vicinity of the support locations. Another indication of excessive support spacing is high vertical support loads. These checks are relevant for sustained load cases. Possible failures for excessive support spacing are ruptures of the piping near the support locations. The next cause of failure is insufficient stiffness in the system. When the system is insufficiently restrained, for instance, when only rest supports are used, the piping can move relatively freely. This is beneficial for thermal loads, but can be disastrous for environmental, cyclic, and dynamic loads. We will discuss the effect of dynamic loads later, so we will focus on environmental and cyclic loads for now. Let's have a look at the top view of the system. We can see that there are no guides in this system. When wind blows past the system, a force is applied to the piping. Since there are no lateral restraints, this could result in significant displacements, as the only thing that keeps the system in place is frictional forces exerted by the rest supports. At sufficient wind velocities, the piping can slide off its rest supports. The same issue arises for earthquakes. An earthquake imposes accelerations on the support structure of a piping system. When there are no lateral supports present, the piping system can slide off its supports as well. One of the most common causes of overstress in static stress assessments is insufficient flexibility. In this case, the piping does not have sufficient room to deflect, resulting in high loads on supports, flanges and nozzles and excessive stress at locations where piping changes direction, such as bends and tees. These high loads are generally caused by thermal effects. So, they will be observed in the expansion and operating cases. There is a wide range of possible failures that can occur when there is insufficient flexibility in the system. Leakage, or even rupture, at weak points, such as welds or deficiencies, at the locations where excessive stresses occur, in flanges and nozzles. Supports could break as a result of the high loads, and the piping can permanently deform. Let's have a look at a few examples where this could be an issue. Let's again look at a top view of the system, and zoom in on the piping near the vessel nozzle. When the temperature in this system is increased to its design temperature, the horizontal pipe will expand in the X direction. This will deflect the connecting lines as well. An exaggerated visualization of the deflection is drawn on the piping system, using an orange dashed line. The connecting lines are connected to the vessel at one side, and restrained by a guide at the other side. This is typically a location of concern when performing the stress assessment. For a sufficiently high design temperature, excessive stress can occur at the tees to the right and the bends to the left, and excessive loads can occur at the vessel connections to the right and the guide support to the left. Leakage, or even rupture, can be expected at the indicated locations as a result of excessive stress, and the support could break as a result of excessive loads.